This video is largely about the kinetic molecular theory of gases and how we handle gas volumes, temperatures, and pressures. So we'll get started with the 5 points of the kinetic molecular theory of gases and then go through how we measure temperature, pressure, and volumes. Okay, first of all, gases are filled with lots of molecules in point 1, and they are constantly moving, they don't stop. And they just kind of bounce off each other, and they bounce off walls of their containers, and they just keep on moving. The volume of the molecules are very small. The size of the space that they occupy is much, much larger. So if we look at the individual size of the molecules, they're actually quite tiny. And in point 3 there, when we see them get close to each other, there's really no forces between them. So what that means is they just kind of slip right past each other. They're not attracted by each other, nor are they repelled by each other, just because there's just so much space that these molecules have to move around in. So we ignore any kind of interactions between the molecules at all. Now what about energy? So when they collide with each other, they do bounce off each other, and elastically is what they're called. So they bounce off and they don't lose any energy. So throughout time, the average kinetic energy of molecules really doesn't change as long as we don't cool the gas or heat the gas at all. So expect the average motion of these molecules to remain pretty constant as long as temperature doesn't change. And again, for question 5 here, talking about temperature, the average kinetic energy is really the energy of motion of molecules, and it's directly proportional to the Kelvin temperature. And any given temperature, the molecules have the same average energy then. We'll be looking at the Kelvin scale in a couple moments here in this video. So let's look at a random sample of gas here. So we have a particle here. Okay, the particles can move all over the place in here, and they bounce off the container. They move around, they can bounce off each other, and so why do these molecules actually exert pressure? They exert pressure because of those collisions. You know, they push against the walls of the container, they push against each other, and they put force per unit area. So if we look at all of the area here that these molecules can push on. So that's why forces create pressure. And we looked at that in our previous lesson about force per unit area. So volume, of course, is the amount of space that's occupied by all of the particles here. Now, again, we're saying that the space that they occupy is much larger, so the small size of these really don't matter. And we also take a look at the small sizes and say, well, this is actually blown up the size so we can actually see it. These molecules would actually be a lot smaller than that. So pressure, volume, and temperature are all considerations. So how do we deal with this? Well, first of all, let's take a look at what atmospheric pressure actually is. There are 4 different ways that we measure atmospheric pressure. The most common in chemistry is in kilopascals. In a previous lesson, we learned that a pascal was a Newton per meter squared. Well, the atmosphere is 101,300 pascals. So it's a lot, and we're pretty used to having that pressure on us. What's it really due to? Again, the molecular motion of the molecules colliding with us. Also, gravity pulling air down. We have to remember that the atmosphere does have an effect caused by gravity too, all pushing down on top of us. We can think of we're at the bottom of the ocean of a very large amount of air on top of us. We can also say it's 1 atmosphere, or 760 millimeters of mercury. I'll be describing this in a moment. And then one that you might be familiar with is PSI, pounds per square inch. It's 14.7 pounds per square inch. So what are gas variables? We use letter V to represent volume, and most often in this class it'll be in liters. P for pressure, and again most often it'll be in kilopascals. There are other pressures that we might use, and then temperature has to be in Kelvin. I'll be explaining why temperature must be in Kelvin. So what's this millimeters of mercury all about? Well, if we look at this apparatus here is known as a gas thermometer. So what we have is a gas inside of a constant volume container here, and we can change the temperature of the gas because it's in water. We can heat the water up or cool it down. And what that does is the molecules escape, come out here and put pressure, force per area, on this liquid here, and this liquid is mercury. And what happens is the mercury gets pushed down here and gets pushed up this side here. And we can measure the height of the mercury, okay, above this level just using a meter stick. Well, if there's 1 atmosphere of pressure in here, the height of the meter stick here of the amount of mercury above it would be 760 millimeters of mercury. So let's call this level 0 here, and this would be 760 millimeters of mercury above it. So why do we use a mercury thermometer? Well, it's a very useful device and to help us get what's called the absolute value scale. So let's take a look at a graph here. A graph of pressure versus temperature is a straight line graph, something you'll be discovering in lab. And if we make a graph of this and get a straight line, and let's say we go to 0 degrees Celsius or whatever, if we extrapolate a straight line back all the way down to 0 pressure, we get a number of negative 273.15. And this is going to be called the absolute value or absolute zero scale, in which case all pressure ceases to happen. You have a pressure of 0. So what does that mean? All energy is gone from the gas, and the particles are no longer moving. They no longer exert any kind of pressure. So this is called absolute zero, or 0 Kelvin. So this is figured out by the apparatus that I showed you before, the mercury pressure thermometer there. So if we look at this, 0 Kelvin then is absolute zero. It's minus 273.15 degrees Celsius. So how do we convert Celsius to Kelvin? Most often we don't put the 0.15 in there. We just take degrees Celsius and add 273 to that and to get Kelvin. So if we're 25 degrees Celsius outside and we add 273 to that, that'll be 298 Kelvin. Now Kelvin is an absolute zero scale and is based on molecular motion. You will not hear me say degrees Kelvin. It's not a degraded scale. Okay, so what does that mean? The degrees Celsius is a degraded scale. It's based on 0 degrees is where water freezes, and 100 degrees is where water boils. And we degrade that into 100 pieces to get from 0 to 100, and then we go below that and above that. The Kelvin scale is, since it's based on actual molecular motion, it is not degraded. So we say kelvins. So I might have 298 kelvins. I don't say degrees Kelvin. And this is why we use the Kelvin scale to calculate pressures and volumes and temperatures for gases, because it's based on actual molecular motion and indeed has an absolute value of 0, okay, to its scale. So we will never use degrees Celsius when calculating anything in gases. You will not get the correct answers because Celsius is based on water freezing and boiling, and it's not based on actual molecular motion, which is what we need to calculate volumes, temperatures, and pressures for gases. I hope that helps. You're going to be doing a virtual lab now, and if you have any questions, please let me know. Hit save.